Hello, welcome back to EELE 461 561. This is the mini lecture associated with the Monday meeting that we usually have on March 30th. Okay, so we're kind of continuing our study here. We're trying to just slow down a little bit and get used to this whole online transition. So we're going to have very short videos, I don't know, maybe we'll call it simple, but it's probably going to be pretty simple today. I don't want to overwhelm you with a whole bunch of stuff, so I just want to get in kind of a mode of watch a little video, do a little simple quiz, do something simple. Okay, so let's take a look at the daily schedule real quick. Here's what you're doing today. You're going to watch my video on crosstalk terminology. We're moving into a totally new module. And then I have a little quiz for you to take that it's just 7 questions just on terminology. And that'll be due on Wednesday before we meet. Okay, so give that a whirl and let's start talking about crosstalk. Okay, so crosstalk is it is the unwanted coupling from one link to another. Okay, so if you have link for data 0 and it's banging away, and you have another link for data 1 and you get too close to data 0, what'll happen is you'll actually get noise that couples from one link to the other. And the coupling comes in the form of electric and magnetic field lines. So if you think about one line, so this would be a microstrip transmission line on a printed circuit board, you're going to have electric field lines, okay? And they couple to the ground plane or the return plane under normal operation. And, they'll come up and go down here and everything's great. But these electric field lines, if you get another piece of metal too close to it, it will absolutely try to couple to it. And this is an interesting situation because this is where we transition from treating everything as a ground. So like when you're in 101 and 201, we talk about a ground. And it's this perfect plane of electrons and it's 0 volts. When you have AC signals, the concept of a ground kind of vanishes. And instead of a ground, what you talk about is a return path. So as a wave propagates down one of these links, what is happening is you're trying to find a path for the charge to return. And the way I think of it is when you charge up a line, you basically are putting energy onto the line in order to separate positive and negative charge. So you're moving electrons and holes around. Well, anytime you move an electron one way, a hole has to go the other way. So that kind of displacement, or you charge the line, that's where you see the voltage, but something's happening somewhere else also to kind of equalize the charge, right? Because charge doesn't exist by itself when you have an electron. Electron moves here, the hole goes there. And so you use a return path rather than a ground. Well, if you think about it like that, then you can return through any other piece of metal as long as there's a path to get back to the source. And so that's what happens here is that at AC, or while you're transitioning, you can absolutely couple onto another piece of metal. Same thing with a magnetic coupling. So if you look at the magnetic field lines, you've got these magnetic field lines that are kind of going around like this on the main signal. And what happens is that they will absolutely induce magnetic fields on another conductor due to mutual inductance. Okay. And what's interesting about it is that they can both exist at the same time. So you can have voltage or current that exists due to mutual capacitance. That's what we call the capacitance between two lines, and mutual inductance. And they can exist totally separate from each other. And the reason that they can both contribute to the crosstalk or the noise on the other line is because of superposition. So remember, superposition in an electrical circuit allows multiple signals to be occurring or being induced, and the net signal you see is simply the sum of them. So that superposition principle is true in crosstalk also. Okay. All right. So you kind of have a feel for what it looks like. There's kind of 2 main classes of crosstalk. One of them is called signal crosstalk, and this is where you think about a wave propagates down a line and you induce a signal on another line as the wave propagates down. And that is, that's your classic signal crosstalk is what we call it. And it's due to the signal path. Okay. And so it's almost like the wave on the main signal can be thought of as a voltage source that's moving down the line. and it's coupling onto the other line. Okay, but there's actually another category of crosstalk called switching noise, and this is due to the return path. So we always think about the signal path, right? So we think about a wave propagating down this signal right here, and it coupling over to here, and we want to look at that with an oscilloscope, let's say. But it turns out that there can be coupling for the return path too, and you see this a lot when you are looking at like packaging. And so packaging, let's say for example, you have like this old school part and it's got, 8 signal lines and 1 ground pin, 1 return pin on the package. And all 8 of those signal lines need to return their ground into the silicon on the chip. And they all have to share 1 ground pin or 1 return pin. And so then they can actually go into that pin and they superimpose and they can cause havoc too. So there's 2 kind of main categories. There's signal crosstalk and then switching crosstalk. Okay. All right. And switching noise, switching noise, the big one is ground bounce. If you've ever heard that term, we'll talk about what that is, but that's kind of the predominant one. Okay. Here is kind of our last thing we're going to talk about with terminology. Actually, let's do this too. We have terms for the 2 links or multiple links. First, the aggressor is the signal that is switching and causing noise on another link. The person receiving or the link receiving the noise, the crosstalk, is the victim. So you have the aggressor and the victim. And you can have multiple victims, okay? You can have multiple victims. But when you do the analysis, you might say, well, isn't the victim switching? And it's like, just, you know what? You do the analysis based on superposition, right? So you always look at what is the aggressor, when it switches, what happens to the victim. Okay, so if you draw this all out, you have a link that has our typical, LC model where you have inductance and capacitance in this form, and you have this infinite number of these, and that kind of builds up the circuit model for a transmission line. Well, you also have mutual capacitance that couples to another line. You have mutual inductance that couples to the other line. And we define the 2 terms where we observe crosstalk as near end and far end. And I just want you to know that's what you call it. So you don't say noise at A. You say, no. We're talking about near end crosstalk. And that just has to do with the node or the location on the line where we observe crosstalk. And of course, we've been calling this VA, but we're going to start using the real terms, which is near end. And then far end, of course, is the end. That's kind of the load. Okay, that's all I got for today. Just a couple terms, and you go ahead and take the little quiz on just the terms that we just talked about, and I will talk to you on Wednesday.